Tonight, we're embarking on a particularly dreamy journey, one that might just change how you think about falling, flying, and the dance between Earth and everything that circles it. Before we drift into the depths of orbital mechanics, I'd love to know where in the world you're listening from tonight, and what time it is in your corner of the universe. There's something beautifully fitting about discussing orbits while we're all scattered across time zones, each of us following our own gentle path around this spinning planet. If you find tonight's celestial voyage soothing, intriguing, or simply a peaceful way to unwind after the day's adventures, I'd be ever so grateful if you gave this video a like, perhaps subscribed, or even left a comment below. It helps this little corner of calm reach other wandering minds who might need a moment of cosmic perspective. Now, I do hope this isn't so fascinating that it keeps you awake, but if it does, well, at least you'll drift off knowing something profound about the invisible forces that keep our world dancing through space. So settle in, let your shoulders drop, take a slow breath, and let's begin to explore one of the universe's most elegant mysteries. Picture this. You're standing at the edge of a very tall cliff, holding a stone in your hand. You release it, and down it falls, pulled by Earth's gravity toward the ground below. Perfectly ordinary, perfectly predictable. But now imagine you throw that stone forward as you release it. It still falls, of course, but it also travels some distance before hitting the ground. Throw it harder, and it travels farther before gravity wins the battle and brings it down. But here's where things get wonderfully strange. What if you could throw that stone so fast, so incredibly fast, that by the time it would normally hit the ground, the curved surface of the Earth had already fallen away beneath it? The stone would still be falling, mind you. Gravity never stops pulling, but the ground it's trying to reach keeps curving away. So the stone falls and falls and falls, but never actually lands. It just keeps falling around the Earth, forever. This, in the most beautifully simple terms, is what an orbit is. It's not floating, it's not being held up by some mysterious anti-gravity force. It's falling, constantly, endlessly, gracefully falling, but moving forward so quickly that the fall never ends. Every satellite, every space station, every moon and planet is locked in this eternal dance of falling without ever hitting the ground. The International Space Station, that remarkable outpost of human ingenuity floating 400 kilometers above our heads, isn't defying gravity at all. The astronauts inside aren't weightless because there's no gravity up there. Quite the opposite, actually. Earth's gravity at that altitude is still about 90% as strong as it is here on the surface. No, they're weightless because they're falling, along with their spacecraft, their experiments, and their floating droplets of water, all falling together toward Earth at exactly the same rate. But they're also moving sideways at about 28,000 kilometers per hour, fast enough to circle our entire planet in roughly 90 minutes. So as they fall toward Earth, Earth curves away beneath them, and they find themselves in a constant state of graceful, perpetual tumbling through space. It's like being in an elevator where the cables have snapped. Except the elevator car is moving so fast horizontally that it never hits the bottom of the shaft. This concept that orbits are simply controlled falling was one of Isaac Newton's most brilliant insights. In his thought experiment, he imagined a cannon positioned on a mountain so tall it reached above Earth's atmosphere. Fire a cannonball with just a little powder, and it follows a simple arc before hitting the ground nearby. Add more powder, fire it faster, and it travels farther before landing. But fire it fast enough, Newton reasoned, and that cannonball would travel all the way around the Earth before gravity could bring it down. completing a full orbit and theoretically returning to the mountain from the opposite direction. Of course, Newton never had access to such a mountain or such a powerful cannon, but his mental experiment perfectly captured the essence of orbital mechanics 3 centuries before humans would actually put it to the test. Every satellite launch, every moon landing, every probe we've sent to explore the outer planets, all of them rely on this fundamental insight. Achieving orbit isn't about escaping gravity. It's about falling with style. The speed required to accomplish this elegant forever fall depends on how high you are and what you're orbiting around. 8 kilometers per second. That's more than 28,000 kilometers per hour. Fast enough to travel from London to New York in about 12 minutes. At that speed, you complete one orbit every 90 minutes or so, watching 16 sunrises and sunsets every day as you chase the Terminator line around our spinning planet. But here's something delightfully counterintuitive about orbits. If you want to catch up to something ahead of you in the same orbit, you don't speed up directly toward it. If you fire your engines to go faster, you'll actually move to a higher orbit, where you'll travel more slowly and fall further behind. Instead, to catch up, you need to slow down first, dropping to a lower orbit where you'll move faster, then speed up again to rise back to the original orbit, but now ahead of your target. It's like taking the inner lane on a racetrack, except the inner lane exists in a different dimension of space and time. This orbital choreography becomes even more intricate when you consider that nothing in space orbits in perfect isolation. The moon doesn't just orbit Earth. It orbits Earth while Earth orbits the sun, while the sun orbits the center of our galaxy, while our galaxy dances with its neighbors in a cosmic ballet of unimaginable complexity. Each body influences every other body, creating a nested hierarchy of gravitational relationships that would make a mathematician weep with joy. The moon's orbit around Earth, for instance, isn't a perfect circle but an ellipse, bringing it sometimes closer and sometimes farther away. When it's closest, at what we call perigee, it's about 356,000 kilometers away. When it's farthest, at apogee, it's about 406,000 kilometers distant. This elliptical dance is why the moon sometimes appears larger in our sky and sometimes smaller, why the tides are sometimes more extreme and sometimes more gentle. But the moon isn't content to simply maintain its current orbit. It's actually spiraling slowly away from Earth, stealing a tiny bit of our planet's rotational energy with each orbit, and using it to boost itself to a higher, more distant path around us. 8 centimeters per year, roughly the same rate at which your fingernails grow. But over the vast spans of geological time, this gradual separation has profound consequences. Billions of years ago, when the moon was younger and closer, it loomed much larger in Earth's sky. The tides were dramatically more extreme, and our planet spun much faster, with days lasting only about 6 hours. The moon's gravity acted like a brake on Earth's rotation, gradually slowing our spin while simultaneously pushing itself into a more distant orbit. It's a beautiful example of the conservation of angular momentum, the same principle that causes a figure skater to spin faster when they pull their arms closer to their body. This tidal relationship works both ways, though much more subtly. Earth's gravity also creates tides on the moon, bulging its rocky surface by several meters, though without water to make the effect obvious. Over the eons, this tidal friction has gradually slowed the moon's rotation until it became tidally locked with Earth, always showing us the same face. The same side of the moon has been facing Earth for millions of years, while the far side, often incorrectly called the dark side, remains forever hidden from our direct view. Most of the planets in our solar system have similar relationships with their moons. Mars has two tiny moons, Phobos and Deimos, named after the Greek gods of fear and dread. Phobos orbits so close to Mars that it's actually spiraling inward rather than outward, doomed to either crash into the planet or be torn apart by tidal forces in about 50 million years. Deimos, farther out, will likely survive much longer, but both moons are probably captured asteroids rather than bodies that formed alongside Mars. Jupiter, the giant of our solar system, hosts a complex family of at least 79 known moons, each following its own orbital path through the planet's powerful gravitational field. The four largest, discovered by Galileo more than 400 years ago, demonstrate the full range of orbital relationships. Io, the innermost, is caught in such a tight gravitational dance with Jupiter and its neighboring moons that the constant flexing and stretching of tidal forces keeps its interior molten, powering the most volcanically active world we know of. Europa, the next moon out, likely harbors a vast ocean beneath its icy surface, kept liquid by the same kind of tidal heating, though less extreme than Io experiences. Ganymede, larger than the planet Mercury, and Callisto, ancient and heavily cratered, complete this system of Galilean satellites, each locked in precise orbital resonances that have remained stable for billions of years. Saturn's moon system is equally fascinating, dominated by Titan, larger than Mercury, and possessing a thick atmosphere and lakes of liquid methane and ethane on its surface. But perhaps even more intriguing is tiny Enceladus, which sprays geysers of water ice from its south polar region, clear evidence of a subsurface ocean that might harbor conditions suitable for life. These distant worlds remind us that orbits aren't just abstract mathematical concepts. They're the fundamental organizing principle that allows complexity and perhaps even life to emerge in the cosmos. Without stable orbits, planets couldn't maintain the steady conditions necessary for atmospheres to develop and persist. Without the moon's stabilizing influence on Earth's rotation, our planet's climate would be far more chaotic, with the poles wandering dramatically over time. The story of orbits is ultimately the story of balance, the delicate equilibrium between motion and attraction, between the tendency of objects to travel in straight lines and the curved space-time that gravity creates around massive bodies. It's a dance that plays out on every scale, from electrons orbiting atomic nuclei to entire galaxies orbiting around the supermassive black holes at their centers. And perhaps most remarkably of all, this dance of orbital mechanics isn't just something that happens to other objects far away. Right now, as you listen to these words, you're participating in it. You're orbiting the center of Earth along with everything else on the planet's surface, completing one rotation every 24 hours. You're orbiting the Sun along with Earth, taking 1 year to complete each lap around our star. You're orbiting the center of the Milky Way galaxy along with the entire solar system, though that journey takes about 225 million years to complete. In a very real sense, you've never not been in orbit. From the moment you were born until the moment you take your last breath, you'll be falling gracefully through space, held in a cosmic embrace by the same fundamental forces that keep the planets in their courses and the stars in their slow, majestic dance around the galaxy's heart. So tonight, as you prepare for sleep, remember that you're not simply lying still in a bed, in a room, in a house on solid ground. You're aboard a magnificent spacecraft called Earth, falling forever around a star, in orbit around the galaxy, carried along by the gentle, inexorable pull of gravity through the vast, dark, beautiful ocean of space. You're part of the dance, part of the eternal falling, part of the strange and wonderful truth about orbits. And isn't there something deeply comforting about that? In a universe that can often seem chaotic and unpredictable, the mathematics of orbital mechanics provides a kind of cosmic reassurance. The same laws that keep the moon in its path around Earth, that guide the planets in their ancient courses around the sun, that hold the entire galaxy together in its slow rotation. These same laws cradle you gently as you drift toward sleep. Sweet dreams, fellow traveler. Now let's explore the invisible architects of the cosmos, the unseen forces that have been quietly shaping everything we see. You've experienced their effects your entire life without realizing it. Every step you take, every breath you draw, every moment you exist, happens within their influence. Yet most of us never truly consider how extraordinary this invisible scaffolding really is. We've journeyed through the birth of galaxies, watched them spiral into elegant forms, and marveled at their cosmic collisions. But none of this celestial drama would be possible without three fundamental forces working behind the scenes, like stagehands in a cosmic theater. They don't seek applause or recognition. They simply do their work, quietly and persistently, holding the universe together. Let's start with the most familiar, yet perhaps most mysterious of these forces: gravity. You know gravity intimately. It keeps your feet on the ground, pulls rain from clouds, and ensures your morning coffee stays in the cup rather than floating around the kitchen. But gravity is far more than Earth's gentle tug downward. It's the great sculptor of the cosmos, the patient artist that has been carving the universe's structure for nearly 14 billion years. Gravity doesn't hurry. It doesn't force. It simply invites. In the early universe, when everything was nearly uniform, gravity noticed the tiniest irregularities in the distribution of matter. A region here with just slightly more density than average, a pocket there with marginally less. While these differences were almost negligible, gravity took note. It began its slow, persistent work, drawing matter toward the denser regions. Over millions of years, these gentle nudges accumulated. Gas clouds that might have drifted apart instead began to collapse inward. The collapse accelerated as more material gathered, creating the first gravitational wells that would eventually become the birthplaces of stars. Without gravity's patient persistence, the universe would have remained a cold, expanding fog of hydrogen and helium, forever dark and lifeless. But gravity's influence extends far beyond simply pulling things together. It shapes time itself. Einstein showed us that massive objects actually warp the fabric of space-time, creating curves and valleys in the cosmic landscape. Near a massive star, time runs slightly slower than it does in the emptiness between galaxies. Near a black hole, this effect becomes so extreme that time nearly stops altogether from an outside observer's perspective. This might sound like abstract physics, but it affects you directly. The GPS satellites orbiting Earth experience time differently than we do on the surface, because they're farther from Earth's gravitational well. Their onboard clocks tick faster by tiny fractions of a second each day. Without accounting for these relativistic effects, your phone's navigation would be off by several kilometers within minutes. Gravity doesn't just pull on matter, it pulls on time itself. Within galaxies, gravity performs an even more delicate dance. It must be strong enough to hold billions of stars in their orbital paths, yet gentle enough to allow those orbits to remain stable for billions of years. Too strong, and stars would spiral inward, creating chaos. Too weak, and they would fly apart, leaving galaxies as brief, scattered sparkles in the cosmic night. The spiral arms of galaxies like our Milky Way exist because gravity creates density waves that ripple through the galactic disk. These waves compress gas clouds as they pass, triggering bursts of star formation that light up the arms like cosmic fireworks. The stars themselves move in and out of these arms over millions of years, but the wave pattern persists, maintained by gravity's steady influence. Yet for all its cosmic importance, gravity remains the weakest of the fundamental forces. A small magnet can overcome Earth's entire gravitational field by lifting a paperclip. The electromagnetic force holding atoms together is vastly stronger than gravity. So why does gravity dominate on cosmic scales? Because it's the only force that always adds up. Electric charges can cancel each other out, but mass always attracts more mass. Gravity accumulates, builds upon itself, and never lets go. But gravity alone couldn't have built the universe we see. It needed help from something even more mysterious: dark matter. This invisible substance doesn't glow, doesn't reflect light, and doesn't interact with ordinary matter in any way we can directly detect. Yet it outweighs all the visible matter in the universe by a factor of 5 to 1. Every galaxy, including our own, is embedded in a vast halo of dark matter that extends far beyond the visible stars. We know dark matter exists because of what it does, not what it is. When astronomers measured how fast stars orbit within galaxies, they found something puzzling. Stars in the outer regions were moving too quickly. According to the visible mass of the galaxy, these stars should have been flung out into space long ago, like mud flying off a spinning wheel. But there they were, happily orbiting in stable paths. The only explanation that makes sense is that there's much more mass in each galaxy than we can see. This invisible mass, dark matter, provides the additional gravitational pull needed to keep those outer stars in line. It's as if galaxies are like icebergs, with most of their mass hidden from view. The beautiful spiral structures we admire in photographs are just the luminous tips of much larger, invisible gravitational architectures. Dark matter doesn't just fill in the gaps. It provides the foundation upon which all cosmic structure is built. In the early universe, dark matter began clumping together long before ordinary matter could follow suit. These dark matter concentrations created the gravitational scaffolding that guided the formation of the first stars and galaxies. Without dark matter's invisible framework, the universe would look completely different, if it would have structure at all. Computer simulations of cosmic evolution show this clearly. When scientists model the growth of structure in the universe using only ordinary matter, they get smooth, featureless results. Nothing like the rich tapestry of galaxies and galaxy clusters we observe. But add dark matter to the simulation, and suddenly you see the cosmic web emerge. Long filaments of matter connecting dense nodes where galaxies form, separated by vast, nearly empty voids. This cosmic web, sculpted primarily by dark matter, spans the entire observable universe. Galaxies aren't scattered randomly through space. They follow the threads of this vast network, like cities built along ancient trade routes. The dark matter provides the highways, and ordinary matter follows, lighting up the intersections with the fire of a billion stars. What makes dark matter even more intriguing is what it doesn't do. It doesn't interact with light, which is why we call it dark. It doesn't clump together as tightly as ordinary matter, which prevents it from forming dark matter stars or planets. It seems to interact only through gravity, making it the ultimate cosmic minimalist, present everywhere, influential always, but never directly seen. Scientists have built incredibly sensitive detectors deep underground, shielded from cosmic rays and other interference, hoping to catch a dark matter particle interacting with ordinary matter. So far, these experiments have found nothing. Dark matter remains as elusive as ever, a ghostly presence that shapes the cosmos while remaining utterly mysterious. It's humbling to realize that most of the universe consists of something we don't understand at all. The third member of our cosmic construction crew might seem like the most unlikely architect of all: black holes. These regions of space-time where gravity has become so strong that nothing, not even light, can escape seem more like cosmic destroyers than builders. Indeed, black holes can be violent, chaotic entities that shred stars and devour anything that ventures too close. But they also play a crucial role in galaxy formation and evolution. At the heart of nearly every large galaxy, including our own Milky Way, sits a supermassive black hole. These monsters contain millions or billions of times the mass of our Sun, all compressed into a region smaller than our solar system. They're not stellar remnants, the collapsed cores of dead stars, but something far more exotic, primordial engines that may have formed in the early universe, through processes we're still trying to understand. For most of their existence, these central black holes remain relatively quiet, occasionally snacking on gas or an unlucky star that wanders too close. But when they do feed actively, they become some of the most luminous objects in the universe. The matter spiraling into a black hole heats up to millions of degrees, glowing brilliantly before crossing the point of no return. This accretion disk can outshine all the stars in the galaxy combined. More importantly, feeding black holes don't keep all this energy to themselves. They blast enormous jets of particles and energy out into space at nearly the speed of light. These jets can extend for thousands of light years, far beyond the galaxy itself, carrying tremendous amounts of energy into the surrounding environment. It's one of nature's most spectacular displays of power and precision. These energetic outflows have a profound effect on galaxy evolution. They heat up the gas in and around the galaxy, preventing it from cooling and condensing into new stars. In this way, supermassive black holes act like cosmic thermostats, regulating the rate at which galaxies can form stars. Too much star formation, and the black hole turns up the heat, slowing things down. Too little, and the jets subside, allowing star formation to resume. This feedback relationship between black holes and their host galaxies is one of the most important discoveries in modern astrophysics. The mass of a galaxy's central black hole correlates remarkably well with the mass of the galaxy's central bulge of stars. This suggests that black holes and galaxies grew up together, each influencing the other's development over billions of years. Black holes also serve as cosmic recycling centers. When they feed, they don't just consume matter. They process it, heating it, enriching it with energy, and eventually returning much of it to the surrounding space. The jets and winds from active black holes carry material far from the galaxy, where it can cool, condense, and eventually be drawn back in to form new generations of stars. It's a cosmic breathing process, with black holes helping to regulate the flow of matter through the galaxy. Even when they're not actively feeding, black holes continue to shape their surroundings through their immense gravitational influence. Stars orbit the central black hole in our galaxy like planets around a sun, but on a much grander scale. These orbits provide some of the strongest evidence for the black hole's existence. We can't see the black hole directly, but we can watch stars speed up as they approach it and slow down as they move away, following the precise trajectories predicted by Einstein's theory of general relativity. The interplay between these three cosmic architects, gravity, dark matter, and black holes, creates a universe of extraordinary complexity and beauty. Gravity provides the fundamental attraction that draws matter together. Dark matter supplies the scaffolding that guides where and how structures form. Black holes act as regulators, controlling the pace of galaxy evolution and ensuring that not everything happens at once. Together, they've built a universe that's both stable and dynamic, structured yet ever-changing. Galaxies form, evolve, merge, and transform over billions of years, all orchestrated by these invisible conductors. The dance is so intricate, so finely tuned, that changing any one element would result in a completely different cosmos. What's perhaps most remarkable is that we've learned all this from our tiny vantage point on a small planet orbiting an ordinary star in the suburbs of a typical galaxy. Through careful observation, clever reasoning, and occasional brilliant insights, we've managed to decode the universe's invisible architecture. We've learned to see the unseeable, to weigh the weightless, and to map the unmappable. As you drift towards sleep tonight, consider that you're held in place not just by Earth's gravity, but by the combined gravitational influence of our entire galaxy, itself embedded in a vast halo of dark matter, all slowly orbiting around a supermassive black hole 4 million times more massive than the Sun. You're part of a cosmic machine so vast and complex that it defies comprehension, yet so precisely balanced that it allows for the existence of stars, planets, and life itself. The invisible architects never rest. Even now, as your eyes grow heavy, gravity continues its patient work. Dark matter maintains its silent vigil, and black holes regulate the cosmic dance. They built the stage upon which all cosmic drama unfolds, and they'll continue their work long after our sun has faded and our galaxy has merged with Andromeda billions of years from now. In the morning, when you wake and feel gravity gently holding you to your bed, remember that you're experiencing just the faintest whisper of the same force that built galaxies, the same influence that shaped the cosmic web, the same invisible hand that has been crafting the universe since time began. The cosmos isn't held together by what we can see, but by what remains hidden. Now I understand what we're building. This is part 3 of your 12-part series on orbital mechanics, continuing the theme of objects falling forever around other bodies. Let me craft part 3 that flows naturally from your existing content, while maintaining the sleepy, contemplative tone. As we drift deeper into our cosmic meditation on falling, let's turn our gaze outward from Earth's embrace to the vast celestial choreography that surrounds us. The moon, our faithful companion, hangs in the darkness not as a static ornament, but as a fellow traveler locked in its own eternal plunge around our world. And yet, this seemingly simple dance between Earth and Moon reveals layers of complexity that would make even the most patient astronomer pause in wonder. The Moon falls toward Earth just as the International Space Station does, just as you would if you stepped off a cliff. But the Moon's fall is grander, more stately, taking roughly 27 days to complete each graceful arc around our planet. At a distance of about 384,400 kilometers, it moves at a more leisurely pace than our low-orbiting satellites, roughly 1,022 meters per second. Still falling, mind you, just falling very slowly around a much larger circle. But here's where our story grows deliciously complicated. The Moon isn't simply falling around Earth in isolation. Earth itself is falling around the Sun, carrying the Moon along for the ride. Picture this, if you will. As our planet traces its yearly orbit around our star, the Moon sketches a curious looping path through space, sometimes ahead of Earth in its solar orbit, sometimes behind, sometimes to the side, but always bound to our world by gravity's invisible tether. This creates what astronomers call the three-body problem. though in our case it's really more of a many-body problem when you consider all the gravitational influences at play. The sun tugs at the moon tugs at Earth tugs back at both, and all the while this entire system is influenced by the gentle gravitational whispers of Jupiter, Venus, and every other massive object in our solar system. It's a cosmic symphony where every instrument affects every other, creating harmonies and resonances that have played out for billions of years. The moon's influence on Earth extends far beyond the romantic notion of tides, though the tides themselves are a perfect example of orbital mechanics made visible. Twice each day, the oceans rise and fall in response to the moon's gravitational pull, creating bulges of water that chase our satellite around the globe. But the sun contributes too, and when sun and moon align during new and full moons, their combined gravitational pull creates the higher spring tides. When they work at cross purposes during quarter moons, we get the gentler neap tides. Yet tides aren't limited to water. The solid Earth itself rises and falls by about 30 centimeters twice daily, though we're far too small to notice this planetary breathing. Even the atmosphere experiences tides, subtle pressure waves that circle the globe in rhythm with celestial mechanics. We live, quite literally, on a world that flexes and flows in response to the gravitational choreography above. This tidal interaction creates something rather poetic. The moon is slowly spiraling away from Earth. 8 centimeters per year, 7 milliseconds per century. 4.5 billion years ago, when the moon likely formed from the debris of a Mars-sized impact with the early Earth, it hung much closer to us, perhaps only 15,000 kilometers away, and our day lasted just 5 hours. In those ancient times, the moon would have loomed enormous in the sky, creating tides hundreds of meters high and perhaps playing a crucial role in mixing the primordial oceans where life first stirred. Now, eons later, the moon has retreated to a more comfortable distance, and this slow dance of separation will continue until, billions of years in the future, both Earth and moon become tidally locked, showing the same face to each other for eternity, like cosmic lovers lost in an eternal gaze. But even this isn't the whole story. Our moon is unusually large compared to its parent planet. Most moons in the solar system are tiny captured asteroids or small icy bodies. Our moon is about 1/4 the diameter of Earth, making the Earth-Moon system almost like a double planet. This unusual arrangement affects the stability of Earth's axial tilt, which in turn affects our climate and seasons. Without the moon's stabilizing influence, Earth might wobble chaotically, creating wild climate swings that could make complex life far more difficult to sustain. Consider Mars, which lacks a large, stabilizing moon. Its axial tilt varies wildly over geological time, sometimes pointing its poles almost directly at the sun, creating extreme climate variations. Earth's tilt varies by only about 2.5 degrees over a 41,000-year cycle, helping maintain the relatively stable climate that has allowed life to flourish and evolve over billions of years. The gravitational relationship between Earth and Moon also creates something called libration, a gentle rocking motion that allows us to see slightly more than half of the Moon's surface over time. Though the Moon is tidally locked, showing us always the same general face, it nods and shakes its head ever so slightly, revealing glimpses of the far side around the edges. This happens because the Moon's orbit isn't perfectly circular, and its rotational speed is constant, while its orbital speed varies slightly as it moves closer to and farther from Earth. All of these intricate gravitational relationships extend outward into the solar system, where planets and moons engage in an elaborate dance of mutual influence. Jupiter's massive gravitational field shepherds asteroids and comets, protecting the inner solar system from some impacts, while occasionally flinging objects our way. The gas giants' moons, Europa, Ganymede, and Io, are locked in a complex resonance where Io orbits Jupiter twice for every orbit of Europa, and Europa orbits twice for every orbit of Ganymede. This resonance pumps energy into the moon's orbits, flexing them with tidal forces that heat their interiors and, in Io's case, drive spectacular volcanic activity. Saturn's rings provide another beautiful example of orbital mechanics at work. Those seemingly solid bands are actually composed of countless particles, each one a tiny moon following its own orbital path around the planet. Shepherd moons patrol the ring edges, their gravity keeping particles in line, while resonances with larger moons create gaps and structure within the rings themselves. The Cassini division, the most prominent gap in Saturn's rings, exists because particles in that region would complete exactly 2 orbits for every 1 orbit of the moon Mimas, and this 2-1 resonance gradually removes particles from that zone. Even more remarkably, we're beginning to understand that these orbital relationships extend beyond our solar system. The thousands of exoplanets we've discovered around other stars often exist in complex gravitational relationships with their siblings. Some are locked in resonant chains where their orbital periods are related by simple ratios, suggesting that planetary systems naturally evolve toward these stable configurations through millions of years of gravitational interaction. The TRAPPIST-1 system, about 40 light-years from Earth, hosts 7 Earth-sized planets in a remarkable chain of resonances. As you move outward from their star, the planets complete 8, 5, 3, 2, 2, 1, and 1 orbits respectively for every 8 orbits of the innermost planet. This creates a gravitational symphony where the planets regularly align and influence each other's orbits, maintaining stability over geological timescales. But perhaps the most profound implication of these orbital relationships is how they've shaped the very possibility of life in the universe. The concept of habitable zones, regions around stars where liquid water can exist on planetary surfaces, is complicated by orbital mechanics. A planet's orbit must be stable over billions of years for life to evolve and flourish. This requires the right combination of planetary masses, orbital distances, and the stabilizing influence of other bodies in the system. Our own solar system's architecture appears to be somewhat special in its stability. Computer simulations suggest that if Jupiter were much larger or in a different orbit, the inner planets might have been ejected or crashed into the Sun long ago. The giant planet's current positions allow the inner solar system to remain stable over the multi-billion-year timescales required for complex life to evolve. This brings us to a humbling realization. Our existence depends not just on Earth's orbit around the Sun, but on the entire gravitational architecture of our solar system. 6 billion years ago, when our solar nebula collapsed under its own gravity, every planet, every moon, every asteroid has played a role in creating the stable gravitational environment that allowed Earth to maintain liquid water and develop the complex chemistry of life. As you lie there in the darkness, perhaps you can feel it. The gentle pull of the moon raising tides in your body's water. The Earth carrying you through space at 30 kilometers per second around the Sun. The Sun itself falling through the galaxy in its own 230 million-year orbit around the galactic center. You are part of this vast gravitational web, a conscious observer of the universe's grandest dance, made of atoms forged in stellar cores and assembled on a world that has been falling through space for over 4 billion years. The moon above, if it's visible tonight, isn't a distant light but a companion world, locked with Earth in an eternal embrace of mutual falling. Together, You and it and everything around you participate in the universe's most fundamental behavior. The endless, graceful fall that creates all structure, all beauty, all possibility in the cosmos. Now we come to the strange truth that binds everything together. The invisible thread that weaves through every galaxy, every star, every grain of cosmic dust. We've spoken of gravity's gentle pull, of dark matter's hidden scaffolding, of black holes anchoring galactic centers like cosmic lighthouses in the void. But there's something more fundamental at work here, something that makes all of this cosmic choreography possible. You see, every object in space, from the tiniest asteroid to the most massive galaxy cluster, is falling. Not falling towards something necessarily, but falling around it. This is the elegant secret that Newton glimpsed and Einstein perfected. Orbit is simply falling with style. Take our moon, that faithful companion that's been with us for billions of years. It's not floating serenely beside us, defying gravity through some mysterious lunar magic. No, the moon is falling toward Earth constantly, every second of every day. But it's also moving forward so quickly that it keeps missing us, sweeping around in that graceful arc we call an orbit. It's like throwing a ball so fast that by the time it would hit the ground has curved away beneath it. This same principle governs everything in the cosmos. The Earth falls around the Sun, never quite catching up, tracing that familiar elliptical path we call a year. The Sun itself falls around the center of the Milky Way, taking about 225 million years to complete one galactic orbit. And our entire galaxy falls through the cosmic web, drawn by the gravitational whispers of distant galaxy clusters. But here's where it gets truly beautiful. These orbits aren't perfect circles drawn with cosmic compasses. They're dynamic, living things that respond to every gravitational nudge. When the moon tugs on our oceans, creating the tides that have shaped life on Earth for eons, it's also stealing a tiny bit of Earth's rotational energy. This causes the moon to spiral slowly outward, growing more distant at about the same rate your fingernails grow. 4 billion years ago, the moon loomed much larger in our sky, and Earth's days were only about 18 hours long. The moon's gravity pulled more strongly on our planet's surface, creating massive tides that may have helped stir the primordial soup from which life emerged. In another 4 billion years, if the sun hasn't expanded to engulf us both, the moon will appear smaller and more distant, and Earth's days will stretch longer still. This gravitational dance extends far beyond our local neighborhood. Every planet in our solar system tugs on every other planet, creating subtle perturbations in their orbits. Jupiter, that gentle giant, acts like a cosmic vacuum cleaner, sweeping up asteroids and comets that might otherwise threaten the inner planets. Its massive presence has shepherded the asteroid belt, keeping those rocky fragments from coalescing into another planet. And beyond our solar system, the gravitational influence of the sun extends in a vast sphere called the Oort cloud, where billions of icy comets orbit in the cold darkness, some taking millions of years to complete a single journey around our star. These distant wanderers occasionally get nudged by passing stars or galactic tidal forces, sending them falling inward toward the warmth of the inner solar system, where they bloom into the spectacular visitors we call comets. But perhaps the most profound realization is this: we are all participants in this cosmic falling. As you listen to these words, you're riding on a planet that's falling around the sun at about 30 kilometers per second. The sun is falling around the galactic center at 220 kilometers per second. Our galaxy is falling toward the Andromeda galaxy at 110 kilometers per second, and Andromeda itself is part of a larger group that's falling toward the massive Virgo cluster. We are, all of us, caught in an intricate web of falling objects, each following the curved space-time paths that Einstein showed us. There's no up or down in space, no fixed reference point, just this endless, graceful falling that creates the structure and rhythm of the universe itself. The strange truth about orbit, then, is that it's not about defying gravity, but about surrendering to it completely. Every satellite we launch, every space station that houses astronauts, every probe we send to explore distant worlds, they all achieve their destinations, not by fighting the fundamental forces, but by falling with such precision that they arrive exactly where and when we intend. And in this cosmic perspective, the phrase "falling asleep" takes on a deeper meaning. As your consciousness gently releases its hold on the day, as your thoughts begin to drift and your breathing slows, you're participating in the same fundamental process that governs galaxies. A letting go, a surrender to forces larger than yourself, a graceful descent into rest. The universe doesn't fight its own nature. Stars don't resist the gravity that forged them. Planets don't struggle against their orbits. They simply follow the paths that physics and time have laid out for them, falling forever through space in patterns so beautiful and complex that we're still discovering new harmonies in the cosmic symphony. So tonight, as you drift toward sleep, remember that you're not just lying still. You're riding through space on a planet that's falling around a star, in a galaxy that's falling through the universe, all of it held together by the same gentle, persistent force that will eventually carry you into dreams. So we've journeyed through the birth of the universe, watched the first stars ignite, and seen galaxies slowly take shape. We've explored how gravity, dark matter, and black holes sculpt the cosmic architecture, and witnessed the slow-motion ballet of galactic collisions. Now, as we drift toward the end of our celestial voyage, there's one more chapter to this story, one that brings us full circle to where we began. The universe is not finished with us yet. In fact, it's barely getting started. Right now, as you settle into your evening routine, galaxies are still being born. Deep in the cosmic web, along those invisible filaments of dark matter we discussed, gas is still condensing, still collapsing under its own weight. New stars are flickering to life in nurseries scattered across space, each one a potential sun for worlds we'll never see. The universe, for all its ancient history, is still very much in the business of creation. But there's something particularly fascinating happening in our corner of the cosmos. We're living through what astronomers call the stelliferous era, the age of stars. It's a golden time, cosmically speaking, when the universe has enough gas to keep making stars, but hasn't yet exhausted its supply. We're not at the beginning of this era, mind you, but we're not at the end either. We're somewhere in the middle, like guests arriving at a party that's been going for a while but still has hours left to run. This timing isn't accidental. The elements that make life possible, carbon, oxygen, nitrogen, iron, were forged in the nuclear furnaces of earlier generations of stars. Those ancient suns lived, died, and scattered their enriched ashes into space, seeding the cosmos with the building blocks of complexity. 6 billion years ago, and here we are, conscious arrangements of those stellar remnants, looking back up at the night sky and trying to understand our place in the grand story. It's humbling, really. Every atom in your body was once inside a star. The calcium in your bones, the iron in your blood, the oxygen you're breathing right now, all of it was forged in stellar cores at temperatures of millions of degrees. You are not separate from the universe, you are part of it, intimately and eternally. When Carl Sagan said we are made of star stuff, he wasn't being poetic, he was being literal. But the story doesn't end with us. Galaxies will continue to evolve, merge, and change long after our sun becomes a white dwarf and our planet is nothing but a memory. The Milky Way's collision with Andromeda, still billions of years away, will create new gravitational dynamics, trigger fresh waves of star formation, and reshape our local corner of the universe. Other galaxies, caught in the expanding flow of space itself, will drift beyond our horizon, their light stretched until it can no longer reach us. Eventually, the universe will enter what cosmologists call the degenerate era. The last stars will burn out, black holes will slowly evaporate through Hawking radiation, and the cosmos will become a cold, dark, nearly empty place. But that's trillions upon trillions of years in the future, a time span so vast it makes the current age of the universe seem like the blink of an eye. For now, though, we live in an age of light. Galaxies spiral and shine. Stars are born in colorful nebulae. And somewhere, on worlds we can barely imagine, other forms of consciousness might be looking up at their own night skies, asking the same questions we ask. What are those lights? How did they get there? Are we alone? And perhaps that's the most beautiful thing about our journey through cosmic history. We're not just observers of this grand story, we're participants. Every time we look up at the stars, every time we build a telescope or launch a space probe, every time we gather around a screen to watch images from the James Webb Telescope, we're continuing the universe's long project of understanding itself. The cosmos spent billions of years becoming complex enough to create beings who could contemplate their own existence. Hydrogen atoms, forged in the first few minutes after the Big Bang, eventually found themselves arranged into neural networks capable of wonder, of curiosity, of love. The universe became conscious of itself through us, and through countless other minds scattered across the galaxies. So as you lie here tonight, drifting towards sleep, remember this: you are the universe dreaming about itself. Your thoughts, your dreams, your quiet moments of wonder are all part of the cosmic story. The same forces that lit the first stars and shaped the first galaxies are still at work in you. Still creating, still exploring, still reaching towards something greater. The galaxies will keep spinning long after we're gone. But for this brief moment in cosmic time, we get to be here, aware and amazed, carrying the universe's capacity for beauty and understanding. We get to be the part of the cosmos that looks back at itself and whispers in wonder, "How extraordinary." And that, perhaps, is the most profound thing of all. In a universe vast beyond comprehension, filled with black holes and dark matter and mysteries we're only beginning to glimpse, consciousness emerged. Wonder emerged. Love emerged. You emerged. The stars are still falling, still orbiting, still dancing their ancient gravitational dance. But now they have witnesses. Now they have meaning. Now they have you, settling into sleep under their gentle light, carrying their story forward into dreams. Rest well, fellow traveler. So now, somewhere in the vast network of dark matter filaments and galactic clusters, we find ourselves at a curious crossroads. The universe has been expanding for nearly 14 billion years. Galaxies have been forming, colliding, and evolving. But something unexpected is beginning to happen. The cosmic dance that has been accelerating since the Big Bang is starting to change its rhythm. We've spent our journey watching the universe grow more complex, more structured, more alive with light and motion. But now, as we drift deeper into cosmic time, we're witnessing the early signs of what cosmologists call the Great Slowdown. It's not a dramatic collapse or a sudden halt, more like a gradual settling. A universe beginning to catch its breath after billions of years of frantic construction. Many of today's galaxies are no longer the bustling star factories they once were. The Milky Way, for instance, forms new stars at only a fraction of the rate it did in its youth. The gas reservoirs that fuel star formation are either being used up, blown away by stellar winds, or locked up in the gravitational embrace of black holes. We're entering what astronomers sometimes call the stelliferous era's twilight, the long, slow dimming of the universe's most productive age. But this isn't a story of endings. Not yet. It's more like the universe transitioning from childhood to adolescence, from the wild creativity of youth to something more measured and deliberate. The most massive galaxies, those grand ellipticals we discussed earlier, have largely finished their star-forming days. They've become cosmic retirement communities, filled with older, redder stars that will burn steadily for trillions of years to come. Meanwhile, smaller galaxies, particularly the irregular ones, continue their enthusiastic star formation. They're like the universe's teenagers, still growing, still experimenting, still bursting with energy and potential. These galaxies will keep the cosmic lights on long after their larger cousins have settled into quiet old age. There's something poetic about this transition. The universe, which began as a smooth, nearly featureless expanse, has spent eons organizing itself into the most intricate structures imaginable. Galactic superclusters stretch across hundreds of millions of light years, connected by filaments of dark matter like a vast cosmic web. And now, having built this magnificent architecture, the cosmos seems to be stepping back to admire its work. Dark energy, that mysterious force we touched on earlier, continues to accelerate the expansion of space itself. Galaxies not bound to us by gravity are receding faster and faster, their light growing redder and fainter with each passing eon. In the far future, perhaps 100 billion years from now, other galaxies will have moved so far away that their light will no longer reach us. The night sky will show only the stars of our own local group, merged by then into a single massive galaxy. But that's still unimaginably far in the future. For now, we live in what might be called the universe's golden age, a time when galaxies are mature enough to be stable and complex, yet young enough to still be vibrant with activity. We can see across billions of light years, witnessing the full history of cosmic evolution, laid out like pages in an enormous book. The James Webb Space Telescope and its successors are showing us galaxies from when the universe was just a few 100 million years old, barely out of its infancy. At the same time, we can observe nearby galaxies in exquisite detail, seeing the intricate patterns of star formation, the graceful spiral arms, the glowing nebulae where new stars are being born. We're living at a unique moment in cosmic time, when both the past and present of the universe are visible to us. And perhaps most remarkably, we're beginning to understand our place in all of this. We're not separate from the cosmic story, we're part of it. Every atom in your body was forged in the nuclear furnaces of ancient stars, scattered into space when those stars died, and eventually incorporated into the disk of gas and dust that would become our solar system. You are, quite literally, made of processed starlight, a walking, thinking collection of atoms that have journeyed across the galaxy and through billions of years to be here now, listening to this story. The galaxies we've explored tonight aren't just distant objects to admire, they're family. Our cosmic ancestry extends back through the Milky Way's long history of mergers and acquisitions, back to the first generation of stars that lit up the early universe, back to the initial ripples in the cosmic microwave background that would eventually grow into the large-scale structure we see today. In a sense, we're the universe becoming aware of itself. Through us, the cosmos has developed eyes to see its own beauty, minds to comprehend its own vastness, and hearts to feel wonder at its own magnificent complexity. We're not just observers of the cosmic dance, we're participants in it, brief but brilliant notes in a symphony that began with the Big Bang and will continue long after our sun has faded to a white dwarf. So as we reach the end of our gentle journey through space and time, from the cosmic dark ages to the age of galaxies, remember this: you carry within you the story of the universe itself. Every breath you take contains atoms that were once part of distant stars. Every thought you think happens in a brain built from materials forged in stellar cores. You are a temporary arrangement of cosmic dust that has somehow learned to contemplate the stars. The galaxies will continue their slow dance long after we're gone. But for this brief moment in cosmic time, we get to witness their beauty, understand their nature, and feel connected to something infinitely larger than ourselves. And perhaps, in that connection, we find not just wonder but a kind of peace, knowing that we belong to this vast, ancient, ever-evolving universe of light. So sleep well tonight, fellow traveler. Dream of spiral arms and stellar nurseries, of dark matter halos and ancient light. Looking at your excellent journey through orbital mechanics so far, I can see we've explored the fundamental physics, the moon's influence, planetary dynamics, dark matter, black holes, and our cosmic interconnectedness. For part 7, let's delve deeper into how orbital mechanics shapes the very structure of our galaxy and the broader universe. We've traced the elegant dance of planets around stars, moons around planets, and witnessed how everything falls gracefully through the cosmos in perpetual orbit. But now, as we drift further into this sleepy exploration of falling forever, let's expand our view beyond our solar system to see how these same principles of orbital mechanics sculpt the grand architecture of the Milky Way itself, and indeed, the entire observable universe. Our galaxy, that soft river of light we sometimes glimpse on clear, dark nights, is itself a testament to orbital mechanics on an almost incomprehensible scale. The Milky Way contains somewhere between 200 and 400 billion stars, each one following its own orbital path around the galactic center, just as our Earth orbits the Sun. But here's where things become beautifully complex. Unlike the relatively simple elliptical orbits we see in our solar system, stellar orbits within the galaxy are far more intricate, influenced not just by the central gravitational pull, but by the combined gravitational effects of billions upon billions of other stars, vast clouds of gas and dust, and that mysterious scaffolding of dark matter we touched upon earlier. Picture, if you will, our sun as it carries us through space. We tend to think of ourselves as stationary, with the universe rotating around us. But we're actually passengers on a cosmic vessel traveling at roughly 230 kilometers per second around the galactic center. At this tremendous speed, it still takes our solar system approximately 225 million years to complete one full orbit around the Milky Way. This period is sometimes called a galactic year, and in this framework, our solar system has completed only about 20 orbits since it formed 4.5 billion years ago. The last time we were in this particular region of the galaxy, dinosaurs were just beginning to emerge on Earth. As our sun orbits the galactic center, it doesn't follow a perfect circle or even a simple ellipse. Instead, it follows what astronomers call a rosette pattern, a graceful flower-like path that oscillates up and down through the galactic plane while simultaneously moving in its great circular journey around the center. This vertical bobbing motion, with a period of roughly 33 million years, carries us alternately above and below the disk of the galaxy, giving us different perspectives on the cosmic neighborhood as the eons pass. But what drives these vast stellar orbits? At the heart of our galaxy sits a supermassive black hole called Sagittarius A star, weighing in at approximately 4 million times the mass of our Sun. This gravitational giant anchors the entire galaxy, but it doesn't act alone. The galaxy's mass is distributed throughout its structure in stars, gas, dust, and that invisible dark matter halo that extends far beyond the visible edges of the galactic disk. All of this mass contributes to the gravitational field that keeps stars in their orbits, creating what we might think of as a gravitational symphony, with each star playing its part in the cosmic composition. The orbital mechanics of our galaxy reveal themselves in the beautiful spiral structure we observe in other galaxies like our own. These spiral arms aren't rigid structures rotating like the spokes of a wheel. Instead, they're density waves, regions where stars and gas temporarily congregate as they follow their individual orbital paths. Think of it like a traffic jam on a circular highway. The traffic jam itself might remain in roughly the same location, but the individual cars are constantly moving through it. Similarly, stars move into and out of the spiral arms over millions of years, but the arms themselves persist as patterns in the gravitational field. This creates a fascinating interplay between orbital mechanics and star formation. As gas clouds orbit the galaxy and encounter these spiral density waves, they become compressed, triggering the collapse that leads to the birth of new stars. The brightest of these newborn stars illuminate the spiral arms, creating the dramatic patterns we see in spiral galaxies throughout the universe. The stars themselves continue their orbital journeys, but the spiral structure remains, constantly refreshed by new generations of stars born in the density waves. The orbital mechanics of galaxies become even more intricate when we consider that galaxies themselves are not isolated islands in space. They too follow orbital paths, bound together by gravity in groups and clusters. Our Milky Way is part of what's called the local group, a collection of more than 50 galaxies bound together by their mutual gravitational attraction. The two largest members of this group, our Milky Way and the Andromeda Galaxy, are actually orbiting around their common center of mass, though this orbit is destined to end in a collision and merger in approximately 4.5 billion years. Even galaxy clusters, containing hundreds or thousands of galaxies, follow orbital mechanics. These vast collections of galaxies are held together by gravity, with individual galaxies following complex orbital paths through the cluster's gravitational field. Some galaxies dive through the dense center of the cluster, their own gas and dust stripped away by the thin but vast atmosphere of hot gas that pervades the cluster. Others follow more sedate orbits in the cluster's outer regions, their stellar content largely preserved. On the largest scales we can observe, even clusters of galaxies participate in the cosmic dance of orbital mechanics. Galaxy clusters are connected by vast filaments of dark matter, creating what cosmologists call the cosmic web. This web-like structure represents the largest scale organization of matter in the universe, and it too is governed by the principles of orbital mechanics, with galaxy clusters following paths determined by the distribution of mass on scales of hundreds of millions of light-years. But perhaps most remarkably, The orbital mechanics that govern these vast structures are fundamentally the same as those that keep our moon circling Earth or the International Space Station falling endlessly around our planet. The mathematics that describe a satellite's orbit also describe the orbit of our solar system around the galactic center, the orbit of our galaxy around the local group's center of mass, and the paths of galaxy clusters through the cosmic web. This universality of orbital mechanics reveals something profound about the nature of reality. From the smallest scales where quantum mechanics reigns, to the largest scales where dark energy drives the accelerating expansion of the universe, there exists this beautiful intermediate realm where the elegant simplicity of gravitational attraction and orbital motion governs the structure and evolution of cosmic architecture. It's a realm where the same physical principles that allow us to send spacecraft to other planets also explain the majestic spiral structure of galaxies and the web-like organization of the observable universe. As we contemplate these vast scales of orbital motion, it's worth remembering that we are participants in all of these dances simultaneously. Right now, as you listen to these words, you are rotating with the Earth, orbiting the Sun, bobbing up and down through the galactic plane while circling the galactic center, participating in the local group's gravitational ballet, and following the grand currents of the cosmic web as it evolves over billions of years. You are falling through space and time in a nested hierarchy of orbital motions, each one carrying you on a journey through the cosmos that began with the first condensation of matter in the early universe and will continue until the stars themselves fade and grow cold. The orbital mechanics that shape galactic structure also help us understand the deep history and ultimate fate of the universe. By studying how galaxies move and interact, astronomers can trace the expansion of space itself, revealing that the universe has been growing larger and more diffuse since the Big Bang nearly 14 billion years ago. The orbital motions of galaxies serve as cosmic clocks, allowing us to measure the age of the universe and predict its future evolution. In the far future, as the universe continues to expand and dark energy drives galaxies ever further apart, the grand orbital dances we observe today will gradually wind down. Galaxy clusters will become isolated islands in an increasingly empty cosmos, their internal orbital motions the last remnants of the gravitational choreography that once connected all matter in the universe. But that future lies trillions of years ahead, an almost unimaginable span of time during which countless generations of stars will be born, live, and die, each following their own orbital paths through the evolving cosmic landscape. For now, we find ourselves in what might be called the golden age of orbital mechanics, when the universe is old enough to have developed complex structures, but young enough that gravity still binds these structures together in an intricate web of orbital relationships. We live in an era when galaxies still interact and merge, when new stars are born in spiral arms shaped by orbital dynamics, and when the cosmic web continues to evolve through the gravitational influence of dark matter, halos following their own vast orbital paths. This perspective transforms our understanding of our place in the cosmos. We are not merely observers of orbital mechanics. We are integral participants in the grandest orbital dance of all. Our every breath, our every heartbeat, occurs within the context of multiple nested orbital motions that connect us to the deepest structures of space and time. We are, quite literally, children of orbital mechanics, born from materials forged in stars that followed their own orbital paths around long-vanished galaxies, destined to continue the cosmic dance until the universe itself grows cold and still. As we drift toward sleep, carried along by the gentle rotation of our planet, let us marvel at the elegant simplicity underlying such vast complexity. The same force that pulls an apple from a tree also guides the majestic spiral arms of galaxies and orchestrates the cosmic web that spans billions of light years. Now that I've gathered all the context from the reference materials and the summary of previous parts, I'll write Part 8 of The Sleepy Scientist. Falling Forever. The Strange Truth About Orbit. Continuing from where the series left off. This part should focus on how orbital mechanics operates across multiple scales while maintaining the gentle, contemplative tone established in the reference videos. We've journeyed through the cosmic dance of gravity, watched planets and moons trace their eternal paths, and marveled at how black holes bend the very fabric of space and time. But there's something deeply beautiful we haven't fully explored yet. Something that ties together every scale of the universe, from the smallest asteroid to the largest galaxy cluster. It's the simple, elegant truth that orbital mechanics doesn't just govern individual objects. It creates a nested hierarchy of motion that spans the entire cosmos. Every orbit exists within another orbit. Every dance is part of a grander choreography, and every falling object is simultaneously held and released by forces acting across multiple scales. Let's begin with something familiar and work our way outward. Right now, as you listen to these words, you're sitting on a planet that's orbiting a star. That much we know. But Earth's orbit around the Sun is just one layer in an intricate cosmic nesting doll. Our entire solar system, Sun included, is racing through space at about 220 kilometers per second as it orbits the center of the Milky Way galaxy. That's nearly 500,000 miles per hour, though you'd never feel it. The Sun takes roughly 225 million years to complete one galactic orbit, a span of time so vast that the last time we were in this position in the galaxy, dinosaurs were just beginning to diversify on Earth. But even that's not the end of the story. The Milky Way itself is falling, gracefully and eternally, in orbit around the gravitational center of our local group of galaxies. And that local group is falling toward the center of the Virgo cluster, which in turn is being drawn toward an even larger structure called the Great Attractor. It's orbits within orbits within orbits, an endless Russian doll of gravitational relationships that extends as far as we can see into the universe. What makes this so remarkable is that the same fundamental principles we discussed earlier, the same equations that describe how the moon orbits Earth or how a comet swings around the sun, apply at every single scale. The mathematics of orbital mechanics are universal. Whether we're talking about electrons in their quantum mechanical orbitals around atomic nuclei, or entire galaxy clusters bound together by dark matter, the underlying physics remains beautifully consistent. Objects fall toward each other under the influence of gravity, but their sideways motion keeps them from actually colliding, creating stable, predictable paths through space and time. Consider the International Space Station for a moment. It's falling around Earth every 90 minutes or so, following the same orbital principles as the Moon, just much closer to our planet. The astronauts inside experience weightlessness not because there's no gravity up there. Gravity at that altitude is still about 90% as strong as it is on the surface, but because they're in continuous free fall. They're falling around the Earth at exactly the same rate as their spacecraft, creating that floating sensation. It's the same principle that governs every satellite, every planet, every star system in the universe. They're all falling, all the time, in perfectly choreographed patterns. This multi-scale nature of orbital mechanics creates some fascinating resonances and relationships. Take Jupiter's moons, for instance. Io, Europa, and Ganymede are locked in what's called a Laplace resonance. For every 4 orbits Io makes around Jupiter, Europa completes exactly 2, and Ganymede completes exactly one. It's like a cosmic clockwork, with each moon's gravity tugging on the others in precise mathematical ratios. These resonances aren't coincidences. They're the result of gravitational interactions over millions of years, slowly adjusting the orbits until they settle into these stable, harmonious patterns. Similar resonances exist throughout the solar system and beyond. The asteroid belt contains gaps called Kirkwood gaps, where asteroids are swept clean by Jupiter's gravitational influence. Saturn's rings show intricate structure created by the gravitational shepherding of small moons. Even the planets themselves show evidence of past resonances, migrations, and gravitational dances that shaped the architecture of our solar system over billions of years. But perhaps the most beautiful example of multi-scale orbital mechanics is how tidal forces work across different systems. We've talked about how the moon raises tides on Earth's oceans, but tidal forces operate at every scale. Jupiter's gravity stretches and squeezes its innermost moon, Io, so intensely that the moon's interior stays molten, powering the most volcanically active body in the solar system. The flexing happens because Io's orbit isn't perfectly circular, thanks to gravitational tugs from the other moons. So the tidal forces vary as Io moves closer and farther from Jupiter during each orbit. On a much larger scale, when galaxies pass close to each other, tidal forces can stretch them into long, graceful streams of stars. The Milky Way is currently shredding several smaller dwarf galaxies that ventured too close, pulling their stars into long tidal tails that wrap around our galaxy like cosmic ribbons. It's the same physics that creates ocean tides on Earth, just operating on a scale millions of times larger. Even more remarkably, these multi-scale orbital relationships create a kind of cosmic stability. The complex web of gravitational interactions between planets, moons, asteroids, and comets in our solar system has remained relatively stable for billions of years. Yes, there are small perturbations and long-term changes, but the overall architecture endures. Jupiter acts like a gravitational vacuum cleaner, sweeping up comets and asteroids that might otherwise threaten the inner planets. The moon's presence helps stabilize Earth's axial tilt, preventing dramatic climate swings. It's as if the solar system has evolved into a self-regulating system, with each component playing a role in maintaining the stability of the whole. This stability emerges from what physicists call the three-body problem and its extensions. While it's relatively easy to calculate the orbit of one object around another, adding a third body makes the mathematics incredibly complex. The gravitational influences of all three objects on each other create a system that can be chaotic and unpredictable over long timescales. Yet somehow, nature has found configurations that remain stable for billions of years. Our solar system, with its multiple planets and moons all influencing each other, represents a solution to an incredibly complex multi-body gravitational puzzle. The same principles apply to star systems within galaxies. Binary star systems, where two stars orbit around their common center of mass, are extremely common in the universe. Some of these binary systems have planets orbiting them, creating even more complex gravitational relationships. There are planets that orbit just one star in a binary system, following figure-8 paths as they navigate the gravitational fields of both stars. There are others that orbit both stars together, experiencing double sunsets, like the fictional planet Tatooine from Star Wars. At the galactic scale, we see similar complexity. Stars don't just orbit the center of the galaxy in simple ellipses like planets around the sun. The gravitational field of a galaxy is lumpy and complex, shaped by spiral arms, central bars, and the uneven distribution of dark matter. Stars follow what are called rosette orbits, weaving in and out of the spiral arms over millions of years. Some stars have highly elliptical orbits that take them far from the galactic center and back again. Others, like our Sun, follow more circular paths, staying roughly the same distance from the center as they orbit. The beautiful thing about all these nested orbital relationships is how they create structure and pattern across the universe. The same gravitational forces that keep your feet on the ground are responsible for the spiral arms of galaxies, the rings of Saturn, and the dance of binary stars. It's all connected, all part of the same fundamental story of objects falling toward each other but missing, creating stable, predictable patterns in the process. This multi-scale perspective also helps us understand some of the universe's most dramatic events. When black holes merge, as detected by gravitational wave observatories like LIGO, they're following the same orbital mechanics as any other binary system. They spiral toward each other, orbiting faster and faster as they lose energy to gravitational waves, until finally they merge in a cataclysmic event that sends ripples through space-time itself. It's orbital mechanics taken to its most extreme conclusion, where the objects are so massive and the gravitational fields so intense that space and time themselves become part of the dance. Even the expansion of the universe can be understood through the lens of orbital mechanics. On the largest scales, the expansion of space is winning out over gravitational attraction, causing distant galaxies to recede from us. But on smaller scales, within galaxy clusters and groups, gravity still dominates, keeping these structures bound together even as the universe expands around them. It's like islands of gravitational stability in an ocean of cosmic expansion. Understanding orbital mechanics at multiple scales also gives us insight into the future of the universe. We can predict, with reasonable confidence, what will happen to our solar system over the next several billion years. The sun will gradually brighten as it ages, eventually becoming a red giant and likely engulfing the inner planets. But long before that happens, the moon will have moved farther from Earth due to tidal interactions. Earth's rotation will have slowed, and the delicate orbital relationships we see today will have evolved into something new. On galactic timescales, we know that the Milky Way and Andromeda galaxies are approaching each other and will likely merge in about 4 billion years. Computer simulations show us what this collision might look like, how the two spiral galaxies will distort each other with tidal forces, trigger bursts of star formation, and eventually settle into a single, larger elliptical galaxy. It's orbital mechanics played out on the grandest stage, a cosmic dance that will unfold over billions of years. Perhaps most remarkably, this multi-scale view of orbital mechanics reveals something profound about the nature of stability in the universe. Despite all the complexity, despite the chaotic three-body interactions and the perturbations from passing stars and the slow evolution of stellar masses, the basic orbital relationships in our cosmic neighborhood have persisted for billions of years. The Earth has maintained a stable orbit in the habitable zone around the Sun. The Moon has kept our planet's climate relatively stable. Jupiter has protected us from many potential impacts. It's as if the universe has found a way to create pockets of long-term stability within the broader chaos of gravitational interactions. This stability isn't guaranteed, of course. There are ways that orbital systems can become unstable, ways that small perturbations can grow over time until they disrupt the delicate balance. But the fact that we're here, that Earth has maintained a stable orbit for billions of years, that complex life has had time to evolve and develop, suggests that these stable configurations are not just possible, but perhaps even likely under the right conditions. As we drift toward sleep tonight, surrounded by this cosmic dance of nested orbits, it's worth remembering that we're participants in this grand choreography. Every atom in your body was forged in the heart of a star that once followed its own orbital path around an ancient galaxy. The calcium in your bones, the iron in your blood, the oxygen you breathe, all of it was created through nuclear fusion in stellar cores and scattered into space when those stars completed their final orbits and exploded as supernovae. You are quite literally made of star stuff that has been orbiting, falling, and dancing through space for billions of years. And now, as you rest here on this small blue planet, you continue that dance, orbiting the sun, orbiting the galaxy, falling forever through the cosmos in the company of countless other worlds, stars, and galaxies, all following the same beautiful, universal laws that govern the motion of everything from the smallest moon to the largest cluster of galaxies. The dance continues, as it always has, as it always will, and you are part of it, connected to every other piece of matter in the universe, through the invisible threads of gravity and the eternal choreography of orbital mechanics. Standing at the edge of the observable universe, having traced the birth of galaxies from cosmic darkness to spiraling cities of light, we arrive at perhaps the most profound realization of our journey. Every atom in your body, every breath you take, every thought drifting through your mind as you listen to these words, carries within it the signature of that ancient cosmic dance. You are not separate from the story of galaxies. You are woven into its very fabric. The carbon in your muscles was forged in the nuclear furnace of a dying star. The oxygen you breathe was scattered across space by a supernova billions of years ago. The iron in your blood was created in stellar cores under pressures so intense they defy imagination. You are, quite literally, made of galaxy stuff, a walking, thinking, dreaming collection of elements that once swirled in the spiral arms of distant star cities. But the connection runs deeper than chemistry. The same forces that shaped galaxies, gravity's patient pull, the delicate balance between expansion and collapse, the endless recycling of matter from one generation to the next. These same forces govern the rhythm of your heartbeat, the flow of blood through your veins, the electrical impulses that fire across your neurons as you drift towards sleep. Consider this. The Milky Way completes one rotation every 225 million years. Since our solar system formed, we've made roughly 20 trips around the galactic center. 20 lazy cosmic orbits while life emerged on Earth, while continents drifted, while forests grew and vanished, while countless species evolved and adapted and dreamed their own small dreams under the same canopy of stars. During our most recent orbit around the galaxy, mammals learned to fly, flowers bloomed for the first time, and somewhere in Africa, early humans looked up at the night sky and wondered what those distant lights might be. They saw the same Milky Way we see tonight. That ghostly river of light stretched across the darkness, though they couldn't have known they were gazing into the heart of their own galactic home. The story of galaxies is also the story of time itself. When we peer into the deepest reaches of space with our most powerful telescopes, we're not just looking at distant places. We're looking backward through time, watching the universe write its own autobiography in light. Every photon that reaches us from those early galaxies has traveled for billions of years, crossing unimaginable distances, surviving cosmic collisions and the expansion of space itself, just to end up here now, carrying news from the universe's childhood. In a very real sense, You are the universe becoming aware of itself. The same hydrogen atoms that once drifted in the cosmic dark ages now form the neurons that allow you to contemplate your own origins. The same gravitational forces that gathered the first stars into galaxies now hold you gently to the surface of a small blue planet, allowing you to exist, to breathe, to wonder about your place in the cosmic story. This is perhaps the most beautiful paradox of our existence. We are simultaneously insignificant specks in an incomprehensibly vast universe, and yet we are also the universe's way of knowing itself, of telling its own story, of falling in love with its own magnificent complexity. Every time you look up at the night sky, every time you feel wonder at the sight of distant stars, you are participating in a cosmic act of self-reflection that has been billions of years in the making. The galaxies continue their ancient dance around us, slowly spiraling through space, creating new stars, nurturing planetary systems, perhaps even other worlds where other beings look up at their own night sky and wonder about their place in the cosmic web. And somewhere in that vast network of stars and dark matter and swirling gas, in the quiet suburbs of an ordinary spiral galaxy, you are here. A temporary arrangement of stellar ashes that has somehow learned to love, to dream, to tell stories about the very cosmos that created you. So as you settle into sleep tonight, remember that you carry within yourself the memory of every star that ever shone, every galaxy that ever formed, every cosmic dance that ever unfolded in the darkness. You are not just in the universe. You are the universe, experiencing itself subjectively, dreaming its own dreams through your consciousness, finding its own peace in your rest. The stars will keep their vigil while you sleep. The galaxies will continue their patient waltz through space. And somewhere in the vast cosmic web, new worlds are being born under alien suns. But right here, right now, in this quiet moment between waking and dreaming, you are both the observer and the observed, the storyteller and the story. A brief but brilliant note in the universe's endless song. Sleep well, fellow traveler. And so we arrive at a profound realization, one that has been quietly unfolding throughout our cosmic journey. We've traced the birth of galaxies from primordial whispers of matter, watched them spiral into magnificent cities of stars, and marveled at their endless dance through space and time. But perhaps the most extraordinary discovery is not out there among the distant spirals and glowing nebulae, but here, in this very moment, in you. You see, we are not separate from this grand cosmic story. We are not observers peering in from the outside. We are participants, integral threads woven into the very fabric of galactic history. Every atom in your body, every molecule that makes up your thoughts and dreams, was forged in the nuclear furnaces of ancient stars. The calcium in your bones, the iron in your blood, the oxygen you breathe, all of it was scattered into space by dying stars billions of years ago, only to be gathered up again by gravity and woven into planets, into life, into you. Think of it this way. When those first massive stars lived their brief, brilliant lives and exploded in spectacular supernovae, they weren't just ending their stories. They were beginning ours. They were seeding the cosmos with the heavy elements that would one day become part of a small blue world, orbiting an ordinary yellow star in the outer reaches of a spiral galaxy. They were creating the building blocks of consciousness itself. And here's where the story becomes almost impossibly beautiful. We are not just made of star stuff. We are the universe becoming aware of itself. Through our eyes, the cosmos looks back at its own history. Through our telescopes, galaxies separated by billions of light years and billions of years in time finally meet in the quiet chambers of human understanding. We are the universe's way of witnessing its own magnificent unfolding. When you gaze up at the Milky Way stretched across a dark sky, you're not looking at something foreign or distant. You're looking at your home, your ancestry, your very essence scattered across the heavens. Those stars that seem so remote have been your companions all along. Their light traveling for years just to touch your eyes. Their gravitational influence helping to shape the very galaxy that cradled the formation of our solar system. The dark matter that holds our galaxy together flows invisibly around and through you. The same physical laws that govern the dance of spiral arms also govern the beating of your heart. The processes that birth new stars in stellar nurseries are echoed in the chemical reactions that spark thoughts in your mind. You are not in the universe, you are the universe, temporarily organized into the beautiful, complex, conscious pattern that is you. And perhaps most wonderfully, you are participating in the ongoing creation story. Every act of kindness, every moment of wonder, every question you ask about the cosmos adds to the universe's growing complexity and beauty. When you love, when you create, when you seek to understand, you are continuing the work that began with the first stars. The endless process of matter organizing itself into ever more intricate and meaningful forms. The galaxies we've explored tonight, with all their spiral arms and glowing centers, their collisions and their quiet evolution, they are not just distant objects of study. They are part of your extended cosmic family. 5 million light-years of space is coming to join its story with ours. In 4 billion years, when our galaxies merge, it will be like a reunion of long-separated relatives, their stars and gas and dust mingling in a slow, graceful dance of homecoming. And even as we drift toward sleep, the universe continues its patient work. Stars are being born in distant nebulae, their first light beginning journeys that may not end until long after our own sun has faded. Galaxies are spinning through their ancient rhythms. Dark matter is weaving its invisible web, and somewhere, perhaps, other conscious beings are looking up at their night sky and wondering about their place in the cosmic story. But you don't need to travel to distant galaxies to touch the infinite. It's here now, in the simple miracle of your existence. In the fact that hydrogen atoms forged in the first moments after the Big Bang have somehow arranged themselves into the extraordinary complexity of a human being capable of contemplating the universe that made them. In the quiet recognition that every breath you take connects you to the great cycles of stellar birth and death that have been unfolding for billions of years. So as you settle into sleep tonight, remember that you are not falling into unconsciousness alone. You are resting in the arms of the cosmos itself, held by the same gravitational forces that guide galaxies through their stately orbits. Your dreams tonight will unfold in a mind made of stardust, and when you wake tomorrow, you will do so as a conscious expression of the universe's ongoing journey toward greater beauty, complexity, and understanding. The story of galaxies is not separate from your story. It is your story, written in light and matter across the vast canvas of space and time. We've journeyed through the grand choreography of gravity, watched dark matter weave its invisible threads, and marveled at how black holes conduct the cosmic symphony. We've seen how objects don't simply sit in space, but perpetually fall through it, tracing elegant paths that connect the smallest particles to the largest galactic clusters. The universe isn't a collection of separate things, but a living tapestry, where everything dances together in endless orbital embrace. But all this cosmic ballet raises a deeper question. one that might surprise you. As we've watched planets orbit stars, stars orbit galactic centers, and galaxies themselves drift through space-time, we've been observing something profound about the nature of existence itself. Every orbital relationship, from electrons around nuclei to moons around planets, represents a delicate balance between opposing forces. It's a dance of attraction and momentum, where stability emerges not from stillness, but from perpetual motion. And here's the beautiful paradox that ties everything together. In a universe where everything is falling, nothing ever truly falls. The Earth falls toward the Sun, but never reaches it, maintaining its orbital dance for billions of years. You fall toward the Earth, but the ground rises to meet you at just the right moment. Even now, as you rest wherever you are, you're falling through space at thousands of kilometers per second, carried along in the Earth's orbit around the Sun, the Sun's orbit around the galactic center. The galaxies drift through the cosmic web. This endless falling, this perpetual orbital motion, is what creates the stability we experience. It's what allows planets to exist long enough for life to emerge, what permits stars to shine steadily for eons, what enables galaxies to maintain their graceful structures across cosmic time. The universe's tendency toward motion, toward falling, toward orbital dance, is paradoxically what makes everything possible. Perhaps that's the most comforting revelation of all. We're not precariously balanced on the edge of catastrophe, fighting against forces that would tear everything apart. Instead, we're participants in an ancient, ongoing dance that has been choreographing itself since the first particles began to move in the early universe. Every heartbeat happens within this orbital embrace. Every breath you take is made possible by the stable dance of Earth around Sun, of atoms within molecules, of electrons in their quantum shells. So as your own orbit carries you towards sleep, remember that you're never truly at rest. You're always in motion, always falling gracefully through space, always part of the cosmic dance that connects every grain of sand to every distant star. The universe doesn't just contain orbits, it is orbits, endless nested circles of attraction and motion, creating the stable foundation upon which all stories unfold. Sleep well, fellow traveler. And so, dear dreamer, we arrive at the final chapter of our cosmic journey, a gentle landing after drifting through 13.8 billion years of time itself. We've watched the universe unfold from its first trembling moment, witnessed the birth of galaxies, and traced the elegant dance of celestial bodies as they fall forever through the curved fabric of space-time. Perhaps you remember where we began, with that simple yet profound truth that everything in the cosmos is falling. Not falling down, not falling apart, but falling gracefully through the invisible architecture of gravity's embrace. The moon falls around the Earth falls around the Sun, our solar system falls through the spiral arms of the Milky Way, and our galaxy itself falls through the vast cosmic web alongside hundreds of billions of others. This is the poetry of orbital mechanics, the quiet symphony that plays across every scale of existence, from the smallest satellites to the largest galaxy clusters, from the debris in Earth's atmosphere to the dark matter halos that cradle entire galactic neighborhoods. Everything moves in this eternal choreography of attraction and motion. We've seen how Isaac Newton first glimpsed the universal nature of this dance, how Albert Einstein revealed its deeper truth as the bending of space-time itself, and how modern astronomers continue to discover new movements in this cosmic ballet. We've learned that orbits aren't perfect circles, but gentle ellipses, that they decay and evolve, that they can be captured and lost, that they tell stories of gravitational encounters across billions of years. But perhaps most wonderfully, we've come to understand that this falling is not chaos, but creation. It is precisely because matter can fall into stable orbits that the universe has structure, that galaxies can form and persist, that solar systems can birth planets, that worlds can harbor life. The same force that keeps your feet on the ground also keeps the stars in their courses and the galaxies in their vast, slow waltz through eternity. Even now, as you listen to these words, you are part of this dance. You're spinning with the Earth at over 1,000 kilometers per hour, orbiting the Sun at 30 kilometers per second, racing through the galaxy at over 200 kilometers per second, and flowing with the Milky Way through the cosmic web at speeds that dwarf our everyday experience. Yet you feel none of this motion because you are part of it, falling freely through space-time just as everything else does. And in this falling, there is profound stability. The Moon has been falling around the Earth for 4.5 billion years, a constancy that has shaped tides, seasons, and the very evolution of life itself. The Earth has been falling around the Sun for just as long, maintaining the delicate orbital dance that keeps our world neither too hot nor too cold for liquid water to flow. These are not precarious balances, but robust, self-correcting systems, the natural result of matter and energy finding their most stable configurations in the curved geometry of space-time. We've seen how this principle extends to the grandest scales, how dark matter provides the invisible scaffolding for galaxy formation, how supermassive black holes help regulate the birth and death of stars, how the cosmic web itself emerges from the interplay of gravity, expansion, and the mysterious dark energy that pervades all of space. The universe is not a collection of isolated objects, but a single, interconnected system, where every part influences every other part through the patient, persistent force of gravitational attraction. Perhaps this is why the night sky has always moved us so deeply. When we look up at the stars, we're not seeing distant, static points of light, but fellow travelers in this cosmic journey. Every photon that reaches our eyes has traveled across space and time to tell us a story of orbital motion, of matter and energy engaged in their eternal dance of falling forever. The ancient astronomers who first tracked the movements of planets were witnessing this same truth, though they could hardly have imagined its full scope. When they spoke of celestial spheres and cosmic harmony, they were grasping towards something real, the profound order that emerges when matter follows the laws of physics across cosmic time. Modern science has revealed the mechanism behind this harmony, showing us that it emerges not from divine intervention, but from the elegant mathematics of curved space-time and the patient work of gravity across billions of years. And what of the future? The orbital dance continues, will continue, for timescales that humble human imagination. The Moon will continue its slow spiral away from Earth. The Sun will continue its stately progression around the galactic center. The Milky Way will continue its approach toward Andromeda. Billions of years from now, when our descendants, if any remain, look up at a night sky dominated by a vast elliptical galaxy born from the merger of our two spiral homes, they will still be witnessing the same fundamental truth we've explored tonight. Everything falls, everything orbits, everything participates in the great cosmic dance. There is something deeply comforting in this continuity, this vast stability that underlies all the apparent chaos and change of the universe. Despite supernovae and stellar death, despite galactic collisions and the accelerating expansion of space itself, the fundamental patterns persist. Gravity continues to shape the cosmos, matter continues to find stable orbits, and the dance goes on. So as you prepare to sleep tonight, carried by the turning Earth on its endless orbit around the Sun, remember that you are not separate from this cosmic story, but part of it. Every atom in your body was forged in the nuclear furnaces of ancient stars that lived and died in their own orbital journeys around long-vanished galactic centers. You are made of stellar remnants, cosmic dust, the recycled matter of countless previous generations of stars and planets, and perhaps even other living beings, all held together by the same gravitational forces that govern the motion of galaxies. In falling asleep, you join a different kind of orbit, the rhythm of rest and waking that has guided life on Earth for billions of years. And in dreaming, perhaps you'll drift through your own impossible orbits, free from the constraints of physics, but still somehow participating in the great mystery of motion and rest, of falling and floating that defines existence at every scale. The universe is vast beyond comprehension, ancient beyond measure, and filled with wonders we are only beginning to understand. But at its heart lies this simple, beautiful truth that everything is connected through the invisible threads of gravity. Everything participates in the eternal dance of orbital motion, and everything, in its own way, is falling forever through the curved space-time that makes up the fabric of reality itself. Sleep well, fellow traveler in this cosmic journey. Tomorrow the dance continues, as it has for nearly 14 billion years, as it will for billions more to come. And you, wonderfully, mysteriously, are part of it all.